Hello and welcome to this video in the Chemistry Unit 6 series, Chemistry Out There, on oxidation and reduction using rusting as a situation where we can put this in context. My name is Mr. Clee. So the aim of this video is that after you've watched it, we should be able to compare the reactivity of magnesium, zinc, iron and tin. We should also be able to describe oxidation and reduction in terms of gain or loss of oxygen. That's about the easiest version. Also, we should be able to explain it in terms of loss or gain of electrons, a little bit more complicated. And I want you to be able to put displacement reactions in context as examples of redox reactions. Okay, here we have one of the simplest versions of a redox reaction. This is an oxidation and a reduction reaction. This is the thermic reaction, where aluminium reacts with iron oxide to form aluminium oxide and iron. Whenever we talk about redox, we're always talking about what is reduced and what is oxidized. We're always talking about the reactants. In this case, the aluminium is oxidized because it has oxygen added to it to form aluminium oxide, and the iron is reduced, it has the oxygen removed to leave iron. When we move on to talk about electrons, it's a little bit counterintuitive, because when we get reduction, we actually get the gaining of electrons, whereas in oxidation we get the loss of electrons. There's a little mnemonic that you can use to remember this. Oxidation is loss of electrons, and reduction is gaining, or oil rig. Here is an example of a displacement reaction. This is zinc reacting with copper sulfate. In this reaction, zinc sulfate is made and copper. It is a redox reaction because one of these things is oxidized and one of them is reduced. In this occasion, zinc is losing electrons, so it becomes oxidized, and the copper is gaining electrons, which means it becomes reduced. It's an exothermic reaction as well because it rises in temperature. Displacement reactions only take place when you have a more reactive metal in a solution that contains a less reactive metal. So magnesium will react with sulfates of all of these three metals. However, iron would only react with tin chloride, for example. It would not react with zinc or magnesium. It would not be able to displace the more reactive metal from the solution. So I'm going to model this reaction here, show you how to construct the half equations, and then I'm going to give you an example that you can try for yourself. Two half equations. First thing to identify, which is my spectator ion? In this case it's sulfate. It's involved in the reaction, but we're not really bothered about it, so I'm just going to, in effect, get rid of it. And then I'm concerned with zinc on this side and zinc on the products, and the copper ion in the reactants and the copper product. So firstly, zinc ultimately forms zinc ions. That's because on the right hand side it's combined with sulfate and it's therefore a zinc ion. In order to do that, zinc has to become more positive. So in order to become more positive, it must lose electrons. How many electrons does it lose? 2 of them, because it becomes 2+, so it's Zn minus 2e minus gives you Zn 2+. The reverse takes place in the copper reaction. We're starting with copper 2+, and we're ending with copper metal. So if we start with copper 2+ and end with copper metal, we're going to need to gain some electrons. We're going to need to gain 2 of them. So that's the half equation for the formation of copper from the copper ions. So here we have the reaction between magnesium and tin chloride. First thing to do is check it's balanced, which it is. Second thing to do is to identify the spectator ion, which in this case is chloride. So for this purpose I'm going to ignore that. Then magnesium. Magnesium becomes magnesium ion. So if that's the case, it's becoming positive, so therefore it needs to lose negatives. It's becoming 2+, so it needs to lose 2-. So Mg minus 2e minus gives you Mg2+. The reverse is true in tin. That's gaining 2 electrons because it's 2+. to become tin metal. The electrons in effect move from the magnesium, where they're lost, to the tin, where they're gained. Right, here's another example for you to try. Don't forget oil rig. Oxidation is the loss of electrons, reduction is the gain of electrons. So look at your two half equations. To start with, you've got chlorine forming chloride ions. So if you've got chlorine forming chloride ions, Cl2 forming 2Cl-. In this occasion, it is becoming more negative. Therefore, it must be gaining electrons. Because there are two chloride ions involved, each with a -1 charge, we're talking about the gain of 2E-. Therefore, the chlorine in this situation is being reduced to chloride ions. The ion, Fe2+, is becoming more positive, Fe3+. Therefore, it must be losing electrons. Because we have 2 of the iron ions here and 2 of the iron ions there, it's the difference between the charge we need to be aware of this time. They're losing a total of 2 electrons. So the 2 Fe2+ minus 2E- gives you 2 Fe3+. Okay, another example, we need to think about our half equations. We're starting with aluminium. Now when aluminium forms ions, it forms Al3+ ions. Therefore, it must be losing electrons, and it must be losing 3 of them, giving us our half equation there. If it's losing electrons, it's becoming oxidized. In the second half of this half equation, we're concerned with iodide ions. The iodide ions that are formed are I-. Beforehand, we're starting with I2. Now, therefore, we must end with 2I-. Because it's becoming more negative, it's going to gain 2 electrons. Therefore, the iodine is being reduced because it's gaining electrons. In summary, simplest form of oxidation is when oxygen reacts with a metal. Reduction is where the oxygen is removed from a metal. Another type of redox reaction is a displacement reaction. More reactive metal displaces a less reactive metal from solution. Oxidation is when electrons are lost, and reduction is where electrons are gained. We can also call that oil rig using our little mnemonic to remember. Moving on to rusting as an example of a redox reaction. What I want you to get out of this part of the video is to recall what's needed for iron and steel to rust, understand that that this is a redox reaction, describe and explain how we can prevent rusting, and include how sacrificial protection works. First thing, essentially, iron rusting is a reaction with oxygen, but it needs to take place in the presence of water. And what you actually have is iron reacting with oxygen in the presence of water to form hydrated iron oxide, which is the rust that we see here. The iron atoms are losing electrons, becoming positive Fe3+ ions. They're becoming oxidized, and the oxygen ion atoms gain electrons, becoming reduced to O2- ions. We can basically put our types of protection against rusting into 2 brackets. We've got our barrier methods and our sacrificial methods. Galvanizing is technically a barrier and a sacrificial method. Barrier methods just stop the water coming into contact with the surface of the iron, stuff like painting it, stuff like coating it with metals or with various different things. Here's an example of a barrier method. In stainless steel, chromium reacts with the air to form chromium oxide. This forms a thin barrier on the surface of the steel that protects the iron within it from rusting. It works a lot like aluminium in that sense. You know, aluminium forms a barrier of aluminium oxide, protective layer, that doesn't happen normally in iron because the iron, the hydrated iron oxide would normally flake off. Here is a galvanized gate. Galvanizing is a little bit more complex. It's essentially sacrificial protection and also barrier method. So you're coating it with a more reactive metal. The more reactive metal is more likely to react with the oxygen in the air when it gets wet than the iron is. So it will react first because it will give up its electrons more easily. It's also a barrier because there's a layer of the zinc that protects the iron underneath from rusting. Sacrificial protection only works when you have a more reactive metal, here's the zinc, attached to a less reactive metal, here's the iron. The more reactive metal will lose its electrons more readily than the less reactive metal, in effect protecting the less reactive metal. That's why it's called sacrificial protection, because the more reactive metal sacrifices itself for the less reactive metal. A tanker ship like this will employ sacrificial protection by having a block of magnesium attached below the waterline. This block of magnesium will give up its electrons more easily than the iron, therefore protecting the iron metal until it is fully corroded, and then the piece of magnesium will need to be replaced. Here we have another barrier method. This involves coating a steel iron can with tin metal. This is good because the tin is unreactive and doesn't react with the food inside the container. However, should the tin become damaged, the sacrificial protection works backwards. The tin is less reactive than the iron, so the iron sacrifices its electrons more easily. You might have also observed this fact if you've ever left a steel fork or something like that inside a can in the fridge. The fork will rust more quickly because it is essentially working as sacrificial protection, protecting the tin that the can is coated with. This slide just summarises what I just said on the previous slide. Tin is less reactive than iron, so it loses its electrons less readily. It's less readily oxidised, so if there is a damage, then the iron provides sacrificial protection to the tin. Finally, in summary, when iron rusts, it does so in the presence of oxygen and when in contact with water to form hydrated iron oxide. It's an example of a redox reaction because the iron is oxidised, it loses electrons, and the oxygen is reduced because it gains electrons. When we're trying to protect things from rusting, we do so by using a barrier in most occasions, like paint or grease. But we can also use sacrificial protection, which involves attaching a more reactive metal to the less reactive iron. The more reactive metal gives off its electrons more easily than the less reactive metal, therefore protecting it. There is a problem with tin, however, because if the tin surface that the iron is coated with gets damaged, then the sacrificial protection works in reverse and the iron rusts more quickly. Thank you very much for watching. My name is Mr. Clee. If you've got any questions about this video or any others in the series, please see me or any of your science teachers.